Let's talk about the number I. The name is a problem from the start. Imaginary. It sounds made up, like a unicorn or a dragon, something you'd find in a story, not in a math textbook. And for centuries, that's exactly how people treated it. A strange, nonsensical quirk of mathematics. A ghost in the machine. But the truth is, E is just as real as the number 1 or the number 3 or pi. A label given by people who are understandably confused. To see why is real, we have to forget its name for a minute. We have to look at what it does. And to do that, we need to go back to a simple problem. What is the square root of 9? The answer is 3, because 3 times 3 equals 9. We can also say 3 is the square root of 9, because 3 times 3 also equals 9. A negative times a negative is a positive. This is a rule we all learn. It feels solid. It makes sense. So what is the square root of 1? This is where everything breaks. What number, when multiplied by itself, gives you 1? It can't be a positive number. A positive times a positive is positive. It can't be a negative number. A negative times a negative is also positive. We've run out of the numbers we know. For a long time, mathematicians just said, no solution. They hit a wall and stopped. It was a mathematical dead end. But some problems wouldn't leave them alone, especially when they were trying to solve certain types of equations called cubic equations. These were complex problems about finding the roots of complicated formulas, and a funny thing kept happening. Italian mathematicians in the 1500s, like Girolamo Cardano, would be working on a problem where they knew the final answer was a perfectly normal, real number. Okay? But to get there, the steps in the middle of the calculation forced them to take the square root of a negative number. It was like needing to build a bridge across a canyon. They were on one side with real numbers. The other side, the answer, was also made of real numbers, but the only way to build the bridge was with these strange imaginary pieces. If they just accepted them just for a moment and followed the rules of algebra, the strange numbers would eventually cancel out and they would land safely on the other side with the correct, real answer. This was deeply unsettling. It was like a mechanic telling you that your car runs because a ghost is turning the crankshaft. You don't believe in ghosts, but the car works. So what do? You start to wonder about the ghost. This is where he was born. Not as an answer, but as a tool. A placeholder. A way to get through the middle of a problem. Mathematicians decided to just define it into existence. They said, let's create a number. We'll call it E. And its defining property will be that when you multiply it by itself, you get 1. So I times I equals 1, or I is the square root of 1, that's it. That's the entire definition. It's not something we discovered in nature. It's something we invented, a new rule for a game. But this happens all the time in math. Think about negative numbers. For a long time, people thought negative numbers were absurd. The ancient Greeks, who were brilliant geometers, had no concept of them. How can you have less than nothing? How can you have negative 3 sheep? It seemed nonsensical. The idea of debt helped. If I have $5 and I owe you 8, my net worth is $3. Negative numbers aren't real in the sense that you can hold 3 coins in your hand. But they are real in the sense that they describe a real relationship. They are a tool we invented to expand what we could do with math. The number 0 had a similar struggle. It took centuries for it to be accepted as a number in its own right. Fractions, too. They are just a way of representing a relationship between 2 whole numbers. Pi is no different. It's an expansion of our number system. It's a new piece on the chessboard. We added it because it opened up new moves. The person who gave it the name imaginary was the philosopher and mathematician René Descartes in the 17th century. And he didn't mean it as a compliment. He was talking about these solutions to equations as being imaginary, as in they don't correspond to any real quantity. The name stuck, and it has caused endless confusion ever since. A better name might have been lateral numbers or rotational numbers, because that's what they really do. To see this, we need to stop thinking of numbers as just points on a line. We all know the number line. 0 is in the middle. Positive numbers stretch out to the right 1, 2, 3, and so on. Negative numbers stretch out to the left 1, 2, 3. It's a one-dimensional world. You can only go forward or backward. Let's think about what multiplication does on this line. If you take the number 2 and multiply it by 3, you get 6. You've stretched it. Now, let's think about multiplying by 1. If you take the number 2 and multiply it by 1, you get 2. You flipped it from the right side of the line to the left side. If you take 2 and multiply it by 1, you get 2. You flipped it back. So multiplying by 1 is the same as a 180-degree rotation on the number line around 0. Hold on to that idea, multiplying by 1 is a 180-degree turn. Now, what is e? We defined it by the property that I times I equals 1. Let's translate that using our new insight. And multiplying by and then multiplying by, again, is the same as multiplying by 1. In other words, doing the I operation twice is the same as a 180-degree rotation. So, what operation, when you do it twice, gives you a 180-degree turn, a 90-degree rotation? This is the profound, beautiful, and world-changing insight. Multiplying by is a 90-degree turn. Suddenly, is not some spooky imaginary concept anymore. It's a geometric action. It's a direction. We had our number line, our east-west road, and he just told us there's a north-south road too. Our one-dimensional world just became two-dimensional. This is called the complex plane. The old number line is the x-axis. We call it the real axis. The new direction, the 90-degree turn, gives us the y-axis. We call it the imaginary axis. A number like 3 is just 3 steps to the right. A number like 4 is 4 steps to the left. A number like 2i is 2 steps up in the imaginary direction. What about a number like 3 plus 2i? It's just a coordinate. It's a location on this new 2D map. You go 3 steps right on the real axis and then 2 steps up on the imaginary axis. That's it. That's a complex number. It's not one number, but 2 numbers, a real part and an imaginary part, joined together. They describe a single point on a plane. The name imaginary is just the name for the vertical axis. We could have called them the red axis and the blue axis, or the x-axis and the y-axis. But history gave us real and imaginary, and we're stuck with it. The imaginary part is not less real than the real part. It's just describing a different direction. It's the difference between telling someone walk 5 blocks east and telling them walk 5 blocks east and then 2 blocks north. Both pieces of information are real. Both are necessary to find the location. This geometric view was a huge breakthrough. It was fully developed by mathematicians like Caspar Wessel, Jean Robert Argand, and especially Carl Friedrich Gauss in the late 18th and early 19th centuries. They showed that these complex numbers weren't strange at all. They were just points on a plane, and they followed consistent, beautiful rules of arithmetic and algebra. They weren't imaginary, they were two-dimensional. Okay, so we've established that can be thought of as a rotation, and it gives us a new dimension to work with. That's a nice mathematical idea, but does it have anything to do with the real world? Is it just a clever game mathematicians play, or does it actually describe something tangible? This is the ultimate test of realness for a mathematical idea. Does it help us understand and manipulate the world? And the answer for E is a resounding yes. In fact, our entire modern world is built on the mathematics of imaginary numbers. You are using them right now. The first major application is in electrical engineering. When engineers work with alternating current AC, the kind of electricity that comes out of your wall sockets, they have a problem. In an AC circuit, the voltage, the electrical pressure, and the current, the electrical flow, are not always perfectly in sync. They are both waves, but one wave might be slightly ahead of the other. This difference is called a phase shift. Trying to describe these shifting waves with regular math is a nightmare. It involves a lot of trigonometry, with sines and cosines all over the place. It's clunky and hard to work with, but engineers realize that complex numbers are the perfect tool for the job. Then they can represent the magnitude of a current, how much there is with the real part of the number, and the phase shift, how it's lagging or leading with the imaginary part. A single complex number can hold both pieces of information. The math suddenly becomes incredibly elegant. Difficult problems in circuit design become simple algebra. These doesn't mean the electricity is imaginary. It means the electricity has a phase, a rotational quality that is perfectly suited to describe. Without complex numbers, designing the power grids, motors, and communication systems that run our society would be vastly more difficult, if not impossible. The phone in your pocket, the computer you're using, the Wi-Fi signal carrying this information, all of them were designed and operate using principles rooted in the math of E. Another huge area is signal processing. Any signal, a sound wave, a radio wave, a medical image from an MRI, can be thought of as a complex mess of different frequencies all jumbled together. A powerful mathematical tool called the Fourier transform allows us to break that messy signal down into its pure, simple frequencies. It's like taking a smoothie and separating it back into its original fruits, and the Fourier transform at its very heart uses complex numbers. The number I is essential to how it works. This process is used everywhere. It's in the software that recognizes your voice. It's in how your phone compresses data to send a photo. It's in how astronomers clean up images from distant galaxies. It's a fundamental tool for understanding any kind of wave or vibration, but the most mind-bending application, the one that truly cements the realness of E, is in quantum mechanics. This is the theory that describes the universe at the smallest possible scales, the world of atoms, electrons, and photons. In our everyday world, described by classical physics, we can know where an object is and where it's going. Everything is certain. But in the quantum world, everything is based on probability. An electron isn't at one specific point. It exists in a cloud of probability. We can only say where it's likely to be. The mathematical object that describes this cloud of probability is called the wave function. And here's the astonishing part. The wave function is fundamentally a complex valued function. It requires imaginary numbers. The central equation of quantum mechanics, the Schrödinger equation, has E right there in it. It's not just a convenient shortcut like it is in electrical engineering. It appears to be a non-negotiable part of the fabric of reality. Physicists have tried to formulate quantum mechanics using only real numbers. They've never succeeded in a way that is as simple and complete. This is a profound statement. The most accurate theory we have about the fundamental nature of the universe requires the use of E. It suggests that at its core, reality has a two-dimensional, rotational character that can only be described using complex numbers. The imaginary number E is not just a tool to describe reality. It seems to be part of the language that reality itself is written in. We can even see the beauty of complex numbers. The Mandelbrot set is one of the most famous objects in all of mathematics. It's an infinitely complex, stunningly beautiful fractal shape. You've probably seen pictures of its swirling, chaotic patterns. That entire shape is generated by a very simple equation, ZES, Z2 plus C. But this equation is iterated over and over using complex numbers. You start with a complex number C, you plug it into the formula, get a new complex number Z, plug that back in, and so on. If the number flies off to infinity, it's outside the set. If it stays contained, it's inside the set. The intricate boundary between these two outcomes is the Mandelbrot set. This visual marvel, a universe of infinite detail, comes directly from the simple rule I2E1. It's a world built entirely on the foundation of E. So let's circle back to the original question. What is E, and why is it real? Is the number you get when you ask for the square root of 1. It is a new mathematical tool, an expansion of our number system. We defined it to solve a problem, and it is real. It is not real in the sense that you can hold the apples, but neither can you hold 3 apples or p apples. The realness of a number isn't about its physical manifestation. The realness of a mathematical concept comes from 2 things, its logical consistency and its descriptive power. I is perfectly consistent. The mathematics of complex numbers follows a clear and unbreakable logic. It doesn't contradict itself. It's a stable, reliable system, and its descriptive power is immense. It's so powerful that it has become indispensable. It describes the behavior of electricity. It describes the nature of signals, and it seems to describe the fundamental workings of the quantum universe. When a tool so perfectly describes so many real-world phenomena, you have to conclude that the tool itself is capturing something real. The I in the equations of an electrical engineer represents a real phase shift in a real circuit. The IE in the Schrödinger equation represents a real aspect of a quantum particle's wave function. The problem has always been the name, imaginary. It plants a seed of doubt. It makes it sound fake. If Descartes had called them transverse numbers, or if Gauss's preferred term complex numbers had been the only one used from the start, we probably wouldn't even have this conversation. We would just see them for what they are, an extension of numbers from a single line into a full, two-dimensional plane. So numbers are concepts. They are ideas we use to model the world. We started with counting numbers 1, 2, 3. Then we needed to represent parts of things, so we invented fractions. We needed to represent debt or direction, so we invented negative numbers. We needed to represent the relationship between a circle's circumference and its diameter, and we got irrational numbers like pi. At each step, we expanded our toolkit. We built a more sophisticated system to describe a more sophisticated world. The number E and the complex plane are just the next step in that journey. They represent the discovery that some relationships in the universe aren't just about more or less forward or backward. Some relationships are about rotation, phase, and direction in a plane. Complex numbers give us a language to talk about these relationships. So, the number I is not imaginary. It's a gateway. It takes the flat, one-dimensional number line we all know and opens it up into a rich, two-dimensional world. And it turns out that our universe, from the electricity in our walls to the atoms in our bodies, seems to love living in that two-dimensional world. We didn't invent I. We just discovered it was there all along, a hidden dimension in the language of numbers, waiting for us to find it. It's real because it works. And in science and mathematics, that is the only kind of real that matters.